Yes, next electrical gate 22 paper problem, problem number 28. This is based on electrical circuits exploiting the resonance condition. It's not a simple series resonance. Okay, so resonance for the given circuit having a capacitor and R and L. Okay, so problem is not talking about the impedance or admittance of the circuit, simply the resonance. Okay, so the resonance frequency is given as 150 kilohertz and the bandwidth is given as 600 hertz. Okay, what exactly it means? So if you excite this by an AC source, say it's Vn, and the circuit is going to draw a current I, and this current is going to be a maximum or minimum at resonance condition. But this current is going to be strictly in phase with the voltage. So voltage phasor and current phasor will be in phase. Okay. So depending on the impedance or admittance of the circuit, the current will be either maximum or minimum. Okay. So that's a point. So with respect to that, so this is going to resemble a band pass system. So then the center frequency of this band pass will be omega naught. Usually we take is your omega. Okay, it may be like this or it may be like this depending on the situation. I'm not getting into the details. So this is your omega naught. Okay, so this is your omega 1 and this is your omega 2. Okay, depending on what you take. Okay, you can take sometimes Z, you can take sometimes Y. So depending on that, you will get. Okay, I'm not talking about who is the Y axis. Okay, right. So this is the omega axis. So this is going to be omega 1 and this is going to be omega 2. Okay, so this is what exactly we call as the bandwidth. Bandwidth is going to be omega 2 minus omega 1, upper cutoff minus lower cutoff. Then the quality of such a circuit is defined as the center frequency divided by bandwidth. Okay, so quality factor of the system is defined as center frequency by bandwidth. That is nothing but usually omega naught divided by omega 2 minus omega 1, higher cutoff minus lower cutoff. Okay. So that is equal to, yes, given omega naught, instead of omega naught, you can write it as 2 pi f naught. And then you can write this as 2 pi f2 minus f1. So 2 pi will get cancelled. You can say f naught by f2 minus f1 if it is in hertz. So it is given in hertz. So f naught is given. So 150 kilohertz. So it is nothing but 150 into 10 power 3. Around that, you have a bandwidth of 600 hertz. F2 minus f1 straight away given. So hertz and hertz will get cancelled. You will get the result. So then the quality factor of the circuit is going to be, our network is going to be, so 150, 10 will get cancelled. So then we have 10 power 3 in that, another 0 will get cancelled. In fact, let me cancel the 2 zeros from this. It is 10. So it is 0. So it is going to be 1500 by 6. So 1500 by 6. Okay, will be the Q factor. Okay, so 1500, once again, a small check. Yes, 1500 by 6. So then we can have, so 2 6s, then it's going to be 30. So it is going to be 5 and then 0 you will get. So 250. Let me have a small confirmation. Yes, that's a number. Okay. So the quality factor of the given network is, so it's high Q closer to infinity. Okay. So when it is highly frequency selective, that's what it means. Okay. So it's a very narrow band pass kind of system. Okay. Yes. Quality factor of 250. So the best answer for this problem is 250. Yeah. Very simple problem. If you remember the basics of even a series RLC resonance circuit, the same concepts we are using here. There you need to take the output across your resistor, then it is going to resemble a band pass. Okay, or you, even if you go by the current drawn, okay, the current will be maximum in a series resonance at the resonance condition, and it will become 1 by root 2 times your maximum current. Like that also you can play, but the circuit is a little different, but still the Q is going to be same in both series RLC resonance as well as in the circuit. Okay, so I didn't talk about exactly what happens to the impedance, straight away connecting to the problem, since the Q is equal to the center frequency divided by the bandwidth. So in filters, especially in band pass filters, the Q is talking about the frequency selectiveness. It is actually a narrow band pass function. Okay, so around center frequency we have only little band of frequency. See that the center is 150 kilohertz, but around that center is 150 kilohertz. Around that you have up of 300, down of 300. That's what I mean approximately. Okay, so only 600 hertz bandwidth around 150 kilohertz center frequency. Okay, such a narrow band pass system it is. Okay, having automatically higher frequency selectiveness, higher quality factor. So quality factor is talking about frequency selectiveness in band pass system, like this system, like this RLC resonance circuit. Okay, even in series RLC resonance circuit. Yes, that's a very simple problem. Directly can connect. Okay, yes, the best possible answer for this problem is 250. So we'll update you with the next problem soon.